Hello everyone, my name is Kristian from Indonesia chapter. Thanks for the opportunity to be here and presenting this material about cloud security improvement through infrastructure as code standardization, the lesson learned from Telkomsel. This is the map of Indonesia, and we have more than 17,000 islands in this country. Perhaps the Bali Island is more popular than the country itself. Telkomsel is the biggest telecommunication provider in Indonesia, serving more than 170 million subscribers across the nations. And as a technology company, our IT team is also transforming and providing digital services to the subscribers. Some of them are Telkomsel as the main self-service applications for consumer, DigiPos for the resellers, Dunia Games for the games community platform, Maxstream for the video streaming, Wahyu for the new youth segment, My Enterprise for the enterprise customers, Orbit for the home broadband platform, and new revenue streams like Kunci for edutech, Vita for health tech, and Majamojo for new games venture. With more and more demand of new digital services, Telkomsel is also transforming the infrastructure from on-premises to the cloud. But the application modernizations and cloud adoptions are also imposing the risk. And we cannot completely eliminate all the risks. What we can do is managing the risk. In the cloud environment, some of the risks are, first, unmanaged attack surface. With more services and components in the cloud and more microservices in the applications, the exposure of attack surface is increasing exponentially. Left unmanaged, we can expose the infrastructure and service until the attack comes. Second, human error. Human error is always a constant risk when building business applications, be it on-premise or in the cloud. And the easiness of provisioning infrastructure in the cloud is making the risk higher. Pointing fingers and blaming people for errors will not help the business more secure. We will need stronger processes and stronger control to manage the risk. Third, misconfiguration. With more different cloud provider used by the organization and different technology configuration, the risk of misconfiguration is also increasing. And fourth, data breach. The cloud misconfiguration and lack of protection can lead to data breach. And data is the most valuable things to the attackers, especially the FII, BII, or PHI. Some approaches to manage the cloud security risks are performing regular risk assessment, since the risks are always here. Prioritize and implementing security controls to mitigate the risk, and document and revisit any risks that already accepted. Threat is an attack against the cloud asset that tries to exploit a risk. Some common threats faced by the cloud security are, first, zero-day exploits. Every computer and software, including the cloud infrastructure, will encounter the threat of zero-day exploits. The zero-day exploits are targeting the vulnerability of software and operating systems that are not being patched by the vendors. Second, advanced persistent threat or APT. APT is sophisticated cyber attack in which the intruders establish undetected persons in the network to steal sensitive data over a prolonged time. The attackers may start using zero-day exploit, go undetected for months, moving from workload to workload and stealing sensitive information. Third, insider threats. It is a cybersecurity threat that comes from within the organization, usually by current or former employee who has direct access to the company network and sensitive information that would help carry out such attack. And fourth, cyber attacks. A cyber attack is an attempt by cyber criminals or hacker to access the company system for altering, stealing, or destroying information. It includes malware, phishing, DDoS, or SQL injection. Some guidelines to protect our cloud assets against the security threat are: follow the secure coding standards when building microservices, double and even triple check the cloud configuration to plug any holes, and perform threat hunting. As part of our cloud journey, in Telkomsel, we also keep improving our security posture. A part of the out-of-the-box infrastructure security from the cloud provider, we need to define more controls on the application layer based on the workload behavior. First of all, we exercise the various workload we deployed on the cloud. Different workload behavior will be categorized as different patterns, such as mobile application, middleware, or big data processing. And then we perform the threat modeling for each workload pattern. For this exercise, we were using StratLM and Mitre attack as the threat modeling reference. Based on the threat identified, we add the security controls required, be it in the policy or the technology controls. The ISC itself, infrastructure as code, we derive from the technology controls requirement for each workload pattern. So different workload pattern might have different template as well. The first step in the cloud security improvement was defining the workload pattern. To define the pattern, we need to agree first. What are the consideration factors? It is important to have clear categorization, since in the organization, sometimes we have different understanding on the definition and terminology. On the business factor, for example, what is the criticality of the applications? Is it mission critical with 5 non-availability requirement and 0 downtime? Or business critical or the others? For the business domain, is the workload categorized as strategic, enterprise support, or other domain in the operation? Billing, revenue assurance, fulfillment might be more relevant for the telecommunication industry, and for other industry might have other categories as well. From the consumer perspective, is the application assessed by internal user, public, or partner only? The data classification need to be considered as well to determine the pattern. Are the applications storing the restricted data like PIR or FFI or not? As we know that data breach is one of potential threat in the cloud infrastructure. And then from the application itself, whether the apps interact directly with end user by GUI or website or mobile apps. Also the functional behavior of the applications. Is it transactional, analytics, middleware, broker, front end, or back end? Another angle of consideration is from the underlying technology of the work itself. Is it monolithic or microservices, containerized or not? Also, the uses of the cloud infrastructure that hosts the applications. Is it IaaS or PaaS or using single CSP only or hybrid multi-cloud? In our exercise in Telkomsel, we decided the workload patterns by considering the user perspective, data applications, and the architecture type. Since we have only total under 30 workloads deployed on the cloud. The more consideration used, there will be more combination of patterns created. After the workload patterns was defined, we analyzed the cloud components used for the workload. For example, the compute, container service, file storage, object storage, database, and or caching service. One of the reference for threat modeling is the StratLM. It is the abbreviation for spoofing, tampering, repudiation, information disclosure, denial of service, elevation of privilege, and lateral movement. Basically, for the defined workload pattern, we need to identify the potential threat on each cloud component. For example, on the file storage, like EFS in AWS, what are the threats that categorized as spoofing, unauthorized access to the file storage, etc. And the exercise is continued and mapped for all kinds of threats in this model. Another threat modeling is the Matrix attack. It is a framework contributed by Matrix organizations, stands for adversarial tactic, technique, and common knowledge. Matrix is the same organization that manages the CVE, common vulnerabilities and exposures. Basically, the Matrix attack is a knowledge base that maps adversarial behavior to specific technique and tactic using during a cyber attack. At the end, it will help organization with the insight to improve threat detection, response, and mitigations. So similar with previous approach using the StratLM, we did the mapping of its technique and tactic to each element of the cloud components. With that, we identified the potential threat to our cloud security posture. For our cloud security case, the threat modeling exercise resulting 270 threats across the cloud elements and 42 relevant techniques based on metric attack reference. We can see from the table example. For each data store element, EFS, Elasticsearch, PostgreSQL, Redis, how many typical threads for each category in threat-LM. Same thing also for other elements. For the external entity means outside the application itself, the process inside the workload, and the data flow between modules inside the applications. On the metric attack perspective, also we see how many potential threats for each tactic and technique on the data flow, data store, external entity, and process. For sure, the number of attack, the number of potential threat for the process element will be the highest because it considers the cloud component inside the workload applications. In the metric attack framework, the organization assets are categorized as enterprise, mobile, and ICS industrial control system. For our case, we refer to the enterprise category. There are many tactics and techniques for each category. For example, in enterprise, there are 14 tactics and 194 techniques, but we can analyze and refer to the relevant ones. Here is the high-level approach of the cloud security improvement we have performed in Telkomsel. For sure, the core is the security principles, which serve as foundational guidelines for securing organizational systems and data. There are principles define the overarching objectives, such as confidentiality, integrity, and availability, guiding our approach to cybersecurity. The workload pattern and threat assessment that we have performed previously is used as the source to define the security control later on. On top of that, we are also referring to the control library, such as the common security best practices and our internal Telkomsel ISMS documents, Information Security Management Standards. Based on those sources, we can define cloud security control required to prevent the threat and adopting best practices. The controls can be categorized in several layers: infrastructure, platform, and application. For example, in the infrastructure layer, manage the VPC configurations, IAM policies, default encryption, and so on. The platform control manage the OS, operating systems, and image hardening, database configurations, container image scanning, etc. And application control manage logging, runtime protection like web application firewall, and apps-to-apps authentication, for example. These controls are implemented in the form of standard reference and the implementation templates. As the implementation are highlighted in the red box here, the references mentioned here can be the standard, policy, or procedure to support the operational team in the organizations. And the technology implementation template are the one that can be helped with the infrastructure as code. What is infrastructure as code? The ISC is the method for managing infrastructure or platform through code instead of manual processes. It is a key part in the cloud computing world, and it allows for automated, repeatable IT operations. We can imagine in the world of cloud, container, and microservices, where we have hundreds or thousands of virtual machines, and we have to manage every single configuration. The ISC works by treating the configuration files as source code files, which allows for codified and repeatable management of infrastructure. Without the ISC, the infrastructure configuration was performed manually, and it is a very time-consuming process. Several ISC providers are Terraform by HashiCorp, CloudFormation, Azure Resource Manager, Google Deployment Manager, and Ansible by Red Hat. In our case, and the widely adopted one is the Terraform by HashiCorp. Even Terraform can be extended to manage the platform in on-premise environment, including network appliance. And one of the reasons is the flexibility and cloud agnostic. It can be used for any cloud providers, different with the CloudFormation that can be used only in AWS environment. And for the Ansible, even it has capabilities to manage infrastructure provisioning, it is best used for software installation and configuration automation, mainly for on-premise hybrid environment. And then, how do we leverage the infrastructure as code for enforcing the security control? If we recall in the previous step in the cloud security improvement approach, we have defined the potential threat and the best practice controls to mitigate the threat for each cloud component. For example, in this table, EKS or Elastic Kubernetes Service by AWS, the control improvement we need to apply is to disable public endpoint access in control plane to reduce attack surface and to enable the logging capabilities. For the EC2 instance component or the virtual machine, improvement to be added is to use new enhanced instance metadata service IMDS version 2 to reduce potential server-side attacks. For the identity access management IAM, we need to add constraint to access permission and reduce write access inside the policy. For the components of RDS, Relational Database Service, the improvements are enabling the deletion protection and to enable the logging. For the S3, the object storage service in AWS, we need to enable versioning, manage the lifecycle policy, and restrict the access only via HTTPS. In the right-hand side, we can see one example of Terraform variable configuration template. This is the template specific for the EKS module. In the configuration, we need to specify the cloud account, region environment, and other detail items. For example, related to the improvement to enable the logging, we add the parameter to specify the log bucket and the access key as well. And for the improvement of disabling public endpoint access, we need to specify the public and private subnet variables. These variables will be referred by the EKS platform for the integration flow. And the configuration is continued for the other cloud components in the Terraform variable. And based on this template, the provisioning process is enforced to include the predefined configuration that already include the security controls. Another feature that is only available in Terraform Enterprise is the drift detection. So if there is any changes in the platform configuration that are different with the Terraform code, or we call it the drift, it will be detected by Terraform automatically and immediately. The actions are also configurable, whether is it information only or prevent any manual changes directly. Some benefits by using ISC for security are, first, the consistency. It can avoid manual errors and ensure the uniform implementation of security controls. Second, the scalability. It can automate the security deployment across large and complex environments. Third, auditability. It can maintain the history of infrastructure and security changes for compliance needs. Fourth, shift left. When embedded to the application deployment lifecycle, it can identify and fix security issue in early stage. And the fifth, cost efficiency. By enforcing the security control upfront, it can help to prevent costly security breach or misconfiguration. Finally, let me quote a reminder for us that security is a journey and not a destination, and it requires continuous effort from everyone in the organization, from detection and prevention to response and recovery, in a keep evolving landscape of threat. Thank you for the attention.